Hi, everybody. It is April 14th, 2021. This is our third general body meeting for Drexel AI, spring term of Drexel. And what we had planned today, we're going to go over GitHub management for new members to kind of go around and discuss how to fork our projects, create pull requests, add and contribute to our work. I just want to say thank you to everyone who contributed to the paper so far. I was actually very surprised when I started sending the links out to people on Sunday, and we got a good amount already finished. I think a page, but a lot of the hard work is done, which is just the structure of the paper. And then next we'll work on more of the specifics. But yet, you're more experienced with than I am on the whole GitHub thing. Would you be comfortable?
Yeah, sure.
Okay. Thank you.
All right, so I could share my screen and then we can go over our GitHub workshop. And while we are doing that, I could also start creating some of the tasks and issues that we're going to do later so that we kind of multitask.
So you had mentioned a conference in which a paper is due this Sunday. It's a small paper, 4 pages. And I know we were planning on splitting up the first work into a couple papers anyway. So, I mean, that was more your call to split it up. What would be the focus of the first paper?
So for
right. What do you think would be 4 pages worth? Maybe encoding proteins, creating the GAN, or
yeah. So once we create the GAN, basically any structure prediction that we might get out of it, I think is worthwhile to publish for that conference. And then we can tweak some of the hyperparameters and so do some like other things, and then we can try to push a second paper.
Okay, I think that's doable. We already have the protein encoding, as I talked about last week. Asamu, you said you have a GAN architecture. Are they easy to build? What implementation have you used, or what package?
Keras.
It's in Keras?
Yeah.
Okay, so it's pretty easy to set up.
Yeah, like there's a bunch like on GitHub too.
And what do you do? Do you have a deep network? Can you do deep convolution as well?
Yeah. If I remember correctly, it was convolution.
Okay. Do you have a GitHub? Do you have one on your GitHub?
No, but I can.
Yeah.
Oh, by the way, I have a question. So for the protein, do you encode it in like a fixed size?
So what I did originally is I wanted to do protein structures that were 10 amino acids long. And the longest amino acid is tryptophan, and it's 7 angstroms long. So what I did is I made a 70 by 70 by 70 grid, and I used that. But when I tried to train it, it was way too large to train that kind of size.
Oh really? 70
yeah.
by 70
Well,
by 70.
yeah. Well, it was also difficult because I had to load in a bunch of samples, right? I wanted to have about 10,000 samples of that size.
Oh, okay. Yeah.
I created a generator function that would only bring in one object into memory at a time, and that helped speed things up a bit. But what I also did is I took that 70 by 70 by 70 grid, and I found the smallest the smallest prism that includes all non-zero values, and I used that for the input. And I did that search for all samples, and that was the input dimension.
All right.
Does that make sense?
So what's the? So the input is not just 70 by 70 by 70. It's like a subsection of that.
It would be the smallest bounding prism that encompasses all non-zero values.
Oh,
Right? So if
okay.
across all samples, if you see that you only need a 35 by 35 by 35 region to include all non-zero values, you're only going to use that. You're not going to include any of the zero values outside of that region.
Okay, but for the purpose of the game, I can just put the 70 by 70 by 70.
You can, yeah.
Okay.
And then I can change those parameters because I have a function that searches through. It takes sample. I have a function that takes samples in and then finds the smallest bounding prism, and that'd be pretty easy.
Okay, and secondly,
It's
do
not in
we?
there. It's in protein structure. Predict is
So,
in my other.
so you're minimizing the size of your input.
Yeah, I am.
Smart.
Okay, and secondly, do we have the list of all proteins which I don't know, are cuttable or something, or like list of? Because I was just wondering, like if the generator generates, but the generator generates are assumed to be like false structures but look similar. So I was wondering if one of those structures can potentially be like a new cuttable structure or something. I don't know.
I guess that's the trick.
Oh, okay, yeah. I guess so.
That is the
Can you
trick.
hear me?
Yeah, yeah.
Okay. Yeah, I also like, are you reading in these samples every time you run your program? Because you could just like encode the samples in binary, and that might get like instead of pre-processing it every time.
Yeah. I stored it into a binary file.
Oh, okay.
And that I basically did the pre-processing step, and then I did the machine learning step. But then I had to use a generator to bring them in, and I think you can give. I think I found a way to like use that with Keras, so it only brings in one at a time. And the paper you sent was Jeff. The paper you sent in response to my idea with autoencoders was good. What I was thinking is that we start with proteins, like are they called noisy autoencoders? Where you take a picture, you take an image, and you insert noise, and you try to find
auto denoisers, I think.
Denoising autoencoder.
So my idea is to take a protein, kind of similar like that. Take a protein, shift the decoy structures a little bit, just a tiny amount, and then try to learn back the native structure. But after you do some training, you iteratively make that randomizing in the protein structure larger and larger until you get to like a very unfolded protein, and then the autoencoder can reconstruct it. So you're effectively training an autoencoder to recognize or to reconstruct or refold progressively more unfolded proteins. That would be the idea. So you start with proteins that are slightly off, and then you train that, and then you move to proteins that are more unfolded. So you're increasing the level of unfoldingness.
That's just like, I feel like once you get to a certain point of adding noise, it's not going to work though, right?
Yeah, but it would be cool to see at what point that it stops.
Why would adding more noise lead to unfolding the protein?
Because you're basically moving the atoms positions, and you're moving them out of space. That's the best way I thought that you can unfold a protein, is by moving atoms. That's
more feasible than just trying to predict structure with GANs, right?
You think so?
I think so, yeah.
But
because coding an autoencoder is easier than coding a GAN.
Okay.
As well.
We can try both. I mean.
I have a question. So the idea for the GAN was to differentiate protein structures based on like if you can cut it or not, right?
Yeah, a function, a well-defined function.
Okay. So I guess the autoencoder is like a separate idea. Okay.
Yeah. I guess I was thinking one morning, and I was like, "Oh, it'd be cool." My ideas come to me when I wake up. Funny.
Something else that I want to ask is, what's our end goal with this paper? Is it just to have a GAN that generates like viable proteins?
It's to understand. Well, I mean, it'd be pretty cool to discover novel proteins. I think that's the end goal of everything. It's also there's some underlying hidden relationship. Like there's a function, there's a bio. This is what I opened up with a while ago. There's a very well defined biological mapping between what a protein looks like and what it does, but the reverse just isn't true. You can't say I want a protein that does this and then you know its structure instantly.
Right.
Like if you say I want to drive a blue car, you can think of models in your head that are blue cars, but you can't do that for a protein.
Oh, okay. So our goal is to get the generator of the GAN to only produce.
Yeah.
protein.
So if
Okay.
in a way, I don't know if you can do this for GANs where you can prioritize the discriminator or generator, where you don't want them to be, I don't know how you would do that. Maybe be more
I was
harsh
thinking like,
on the generator.
Oh, so you're thinking that it's a possibility that we could have a GAN that generates a protein with a certain function?
That would be the best thing. That would be really cool. We'd make a lot of
Get it.
money, I'm sure. Something like
we could
that.
get a Nobel for that.
That's what I'm saying.
I don't think you can prioritize GAN section of it. Like
I wasn't sure.
GAN.
I think the learning process is like,
It's balanced.
well, yeah, I mean, like they make each other better over time.
I wasn't
Yeah,
sure
but-
if you like put you're less conservative with one compared to the other, if it makes the other one better, right? Because if two people are like fighting, or if two people are like playing a game, right, and one person is stronger, it's gonna beat up the other one a lot more. I guess it's the idea for like zero. It's a zero-sum game, I think.
Yeah, but like in this situation, I think one of the players has information about the moves that the other player's doing, I guess.
Okay.
Because like you're using the discriminator output to train the generator.
I thought the point is that the two neural networks like get stronger and make each other stronger.
Yeah,
like,
they do.
Yeah, but we don't. It's a the direction is only. It's not double-sided, right? So you could have multiple functionalities that would map, or given a functionality, or given a structure, you can get the functionality. Given a functionality, you cannot get the structure. That's the whole point, right?
Yeah.
So how
It's
would
not, it's not a one-to-one. That's where the
Yeah.
noise comes into the generator. Right?
So exactly. So best we can do is try to learn one of many potential structures, and
Yeah.
the best way of doing that is to iteratively start with a noise, iteratively remove noise one by one until hopefully you find a structure that is feasible. And if it
Yeah.
fails, you do another grid search, maybe start another noise removal process.
oh,
And then if it fails, do another one. Because remember, it's not one-to-one. There could be many functionalities mapping to a very similar structure,
Mm-hmm.
right? So
oh, Ethan,
Sure.
I have one question. So given a structure, can we kind of like know what functionality it has?
Yeah, I mean,
Okay.
those are very well
Okay.
annotated, actually.
And then I think we can replace the discriminator with that. So like given a structure, it can differentiate whether
Those
it's,
are
like,
only for
cuttable
known
or not.
those are only for known structures.
Only for now. Okay.
Yeah, and I'd be very surprised if our generator generates known structures. Because effectively, what that's doing is that's generating real proteins from noise, right?
you also have what's called a principal component analysis of PCA. So you can think of it like taking a bunch of faces for different people and kind of averaging them to get the average of those people. You could do PCA for that and get the average person, average looking person. So we could start with 50 structures and then average them. I don't know what that would be. Probably some
Like 50 structures with a given function.
Yeah, that'd be the idea. Yet I think that so like the PCA is good, but often with proteins and structures, we work with contact maps, which is just if you have n atoms in a protein, You have it's an n by n matrix of pairwise distances between the atoms. And then you can use that to reconstruct the protein structure. That's at least how I did it in my paper, and I think other people do it like that too. So maybe if you find an averaged, you align all the protein structures A, B, you find the averaged contact map, and that would tell you maybe what the structure looks like. Maybe
So
that's a good way of doing it.
What's an average contact map? Is it just the average of distances between each pair?
Yeah.
So if you have like 100 pairs, you have 100 distances, you just average them. But the pairs might have different elements inside them, right? So it could be carbon, carbon, oxygen.
So for fixed amino acids, yeah.
What's a fixed amino acid?
I mean, you have the same amino acid chain. It's just the same amino acid chain. But in a lot of papers, like the one that Jeff sent me, they only looked at this paper that was published in 2020. They only cared about the alpha carbons, which is just the carbon attached to the radical group. So it was all the same atom. And that's really what most people do anyway. That's what my advisor told me back in the summer, that they only look at alpha carbon. So it'd only be one atom type.
Yeah, I think that's more feasible than like generating new proteins from nothing.
I think that if you're mapping, I think that changing it to generate and discriminate contact maps would be better. But you can still encode the features. That's what I did. You can still encode the features into that grid structure and use that to predict the contact map or to generate the contact map. I guess you don't even need a grid structure if you're going to generate the contact map.
Yes.
When you're talking about PCA, are you envisioning that like the n most principal components are going to be features of these proteins that are common among all of them that have the same function, and then like you can build new ones based on like just preserving those, or is that?
Yeah. So you take what is the most important component, let's say. I actually don't know what that component would look like.
Yeah, that's what I'm wondering also.
That component is too much of an abstraction. Because for PCA, for facial images, it's just pixels. For distances, if you have 100 pairs, don't you get, if you have 100 different distinct pairs, each distance between them, you're going to get 100 by 100 matrix, right? So I guess that could be our image. So what I was saying with PCA is that, let's say you have these images or structures, you rank the components that make those structures, but I actually don't know what that like make means, but let's for now just assume that we can create a bunch of components or separate it into a bunch of components. So you then rank them, and then you pick top, let's say, most important n components of them. So then you can start with that and keep adding new like noise to that in the hopes that you're gonna get a new structure.
Okay. You're adding it to the original protein so that the PCA looks different, or the end components of the PCA.
The end component of the PCA, yeah. You're adding to the average of those components because you need a starting point. Average might be a good starting point, and then right, you need a starting point to generate a structure. So the starting point would be the average of those components, and you add some noise to get the component new structure, and then you can learn that because each functionality will map to a structure. So how far you're off would then maybe can be used to penalize your addition. And then maybe you can try to go in a way that would minimize the error, but this is like too much of an abstraction. I actually don't know if it's possible.
Okay, so we have a lot of ideas. Which one is doable by Sunday? I think that it'd be a good place to start would just be throwing some structures at a GAN and seeing what happens. We have people who can help with that.
Okay.
Yeah.
in the data set, I think one of the first things that we need to get is the data set.
Yeah, I can generate that very easily.
So
That's something I can do. What I'll do is I'll generate the protein. I'll generate there'll be binary files, and I'll probably just generate a data set. Yeah, and they'll all be real images, right? They'll all be real structures.
Right.
Do we want to restrict ourselves with the size of these structures? What do we want to do?
Oh, can you make it like seven of them 70 by 70 by 70?
Okay.
Yeah.
So I'll do.
Or like the smallest,
Yeah. Okay, let's do. Because 11, my model over the summer did very well with 10 amino acids. Let's try 15 amino acids. And I might change that later, but 15 amino acids. And then I'm going to restrict myself so that's only alpha helices. So we're only looking at stretches of protein structures that are alpha helix, that are of that secondary structure. And basically in protein files, you have this. Sorry, in protein structures, you have annotation per amino acids, whether it's what secondary structure it is. One thing that I want to include that I haven't been able to look into because I just haven't had time is there's something called torsion angles. And I want to include that as a metric because that tells you, it basically describes, it's an angle or it's a set of angles that describes the relationship between 4 adjacent atoms in molecules. So if anyone's interested, just speak up and research torsion angles because I haven't looked into that. And I would like to include that as a feature.
what's the name of that again?
I think they're called torsion angles.
Torsion.
I have some papers on it too. So I could send it to people. Yeah, it is a torsion angle. Or dihedral torsion angles. That's it. Dihedral torsion angles. What's this, Jeff? Yeah, torsion angles. There it is. That's it. I think it might be 3. Yeah, 3 consecutive bonds involving 4 atoms. Basically, we'd want a way to calculate it. I might even have a function that calculates it in my work. I probably do.
What are we gonna do with these torsion angle calculations?
You're using it as a feature, right? So the
Okay.
idea is that you have that 3-dimensional grid structure, and then you're adding in the information. So what we're probably going to start off with is just the carbon atoms, and then the occupancy value, and then the torsion angles. So there'll probably be those features for each atom.
And we need to, sorry, go ahead.
And then I was going to say we can decide whether we would just want to focus on alpha carbons or if we want to do other atomic atom types as well. That paper that was published that Jeff sent me was just alpha carbon. So it might be worthwhile for this one just to focus on that first.
Yeah, whatever is the simplest at this point should be
Yeah.
the one first 2.
So 15 amino acids long, alpha carbon. So that's 15 alpha carbons with torsion angles. That's something I didn't include in my past work.
So that means one sample in the data set will have 15 columns, or?
One sample in the data set will have 15 coordinates. 15. There'll be 15 coordinates in.
To represent each of those carbons, right? Or am I getting it wrong?
A single sample will be represented by 70 by 70 by 70 grid. There will be approximately 15 of those
occupied, right?
Yeah, 15 will be occupied.
Okay.
So 70 by 70 by 70 is pretty overkill. But it's to
How are we gonna do this 70 by 70 by 70 as input to the GAN?
Oh, I was thinking like images are like 256 by 256 by 3 because of channels, right? So I thought you can
That's
just
what I
do
did.
convolution or something.
Just flatten it.
Yeah.
Yeah.
Honestly,
Okay.
I'm wondering, is it valid to decides those scans? Decides those 70 by 70 by 70?
Can I just show you what I did?
Okay.
Yeah,
Yeah.
let me stop
I also
sharing.
don't think you can flatten it like that because you lose
Yeah, I
you
guess
lose
so.
the dimensional relationships between things that were consecutive. Like if you have a third dimension, then like things that were consecutive with the z-axis are gonna not have.
Yeah,
the
this
same
is one of my 3D CNNs, and when you have this, I think it was just a relatively simple. I didn't know very much about doing the whole TensorFlow stuff back then, but this is what I did. So I didn't flatten it. I didn't flatten until the end.
If you should import this code.
It's there. Like this one is what creates boundaries. So it finds the given new bounds and old bounds, return the updated bounds, fix find bounds. I used all this, didn't I?
How do you use the updated bounds? Like,
This is a good question.
yeah, because I was thinking like we can't have different sides and representations across both sides.
Yeah. So basically I'm finding this function load feature dimensions. What it does is it finds the bounds for a given, what I call entry. And then I update the bounds depending on whether they're smaller than the current bounds. And then what you get is just the, given a set of files storing objects in the identification, return the feature dimension, such as the positional atom types for bound and bounds of the matrix. So what this gives you, given a list of files in a directory, it gives you the smallest rectangular prism that encompasses all of the non-zero elements.
Oh, for every single atom, every single body.
Yeah, it's for every single one. This is across all samples. So then you know how, at the very least, what your architecture has to look like or how big it has to be for the input layer.
Okay, so where did the 70 by 70 by 70 come from? Why not just
it came from a naive calculation that the longest amino acid is tryptophan, which is 7 angstroms long, and I wanted to do this on proteins that were 10 amino acids, so I just did 7 by 10.
Oh, gotcha.
70, and that would get the longest stretch of it. That's the worst case scenario, but in reality, that never happens.
Oh, okay. Yeah, honestly, now that I think about this 70 by 70 by 70, it's the closest way to go out of memory.
Yeah, it is. But yeah, and then there were some other ones. I had one that was one-dimensional with a convolution, one that was three-dimensional, three three-dimensional actually. But yeah, this is all in my master branch for protein structure prediction. And then I showed this last week, but basically how I store everything in proteins, that structure is all here, and then how I convert it is also here as well. So A, data set. B,
You need to
figure
push
out a
the
way.
skeleton, like the template for the GAN.
Yeah.
Code.
Okay.
Samu, how difficult would that be?
Well, I think I might finish today after dinner. Yeah.
Okay.
I don't know.
Sure.
Maybe even tomorrow. I don't know.
Oh, okay. Yeah, it'd be great if we can get data in by tomorrow night.
I might train it on like a MNIST.
Yeah, sure.
Yeah.
Sure.
Instead of the 70 by 70 by 70.
Just make sure it works. And then I'll have to dig back into my code to figure out how I only brought in I use a generator function to bring the samples in one at a time.
Yeah,
data.
honestly, like the TensorFlow documentation or like the class documentation had a GAN, so that's what my code was
Oh.
based on.
And then when I did this research over the summer, I didn't run it on my laptop. I didn't even run it on Drexel because Drexel didn't have I didn't like how they limit all their nodes to 256 gigabytes. So I used Chops Network. I use their service because I work there. So one of the pros.
Oh, did they have GPUs?
Oh yeah.
Oh, okay.
Yeah. They have like an HPC, high performance computing. You can submit a job to one of their servers, and just so fast.
That's awesome.
You could probably rent some server time or something.
Yeah, I tried that on Google, but it just didn't work as well, and I ended up forgetting to unlink my credit card, so I was docked $40.
Wait,
So,
is it something? Is Chops thing something like Google Colab or Paperspace?
No, it's completely through Linux.
Yeah.
So like you just run code like straight on your computer and
Yeah,
the
I
GPU
SSH in, and then boom.
Drexel has a GPU workstation as
Yeah.
well at CCI, but
Is it good?
You have to pay, don't you? You have to pay for something through Drexel.
Drexel,
Yeah.
Drexel.
Or was that,
if you're a
or
student,
was that just for storage?
We could use like SAFAC funding or something, but
Yeah.
no, there's, it's free. You just SSH.
I was
host
just gonna
name.
use Chops.
Okay.
Just won't tell anybody.
Well, you could always use Google Colab as well.
Yeah, I know.
And this is my computer.
Does Google Colab can you run it like straight from your computer, or do you have to like put the code into their thing?
Oh, that's something else I didn't like. You have to upload data, and I don't like that. It takes forever.
Yeah.
Yeah, you could put the data to your Google Drive and then mount the drive
That's
to the
fast.
notebook.
Yeah.
Yeah, but
Too
the
much
one thing
fast.
that's horrible is when it times out.
It does time out, yeah.
Yeah.
Okay, so I know we were supposed to talk about GitHub, but that didn't happen. we got diverged. That's okay.
Yeah, it's okay.
Is anyone unfamiliar with GitHub? I should have asked that in the beginning. You can speak up if you
raise
are.
your hand in the chat.
If you
If
know
not,
how to
it's
do
fine.
git push, git pull, and git clone, add something and create a pull request, I think that's all you need.
Yeah. Okay. Just making sure.
Okay.
Look it up.
Cool. All right. So then we'll
So
look into.
That
Sorry?
concludes the workshop.
Does-
Thanks, everyone.
All right, guys. Here's the workshop. Go to Google, type in how to use Git, and click on the first result.
Okay. And then a lot of the paper was done, actually. Well, I mean, not a lot of it, but a lot of I was very impressed, very happy. Page done. And we'll have to talk more about, obviously, the model architecture. That'll be a Samu's game. Maybe whoever wants to look into dihedral or whatever angles can include that as like an explanation of the features we're using. I can talk a bit more about the biology and the one to many, many to one relationship we're kind of trying to tackle.
I can look at this dihedral stuff if you want.
Okay, yeah, if you wouldn't mind. It's a little molecular. Get your hands dirty. Cool. Does anybody have any questions?
Sam, if you need help with that GAN, I can help as well.
Yeah, thank you. Like if I'm going to any trouble, I will contact you.
Okay.
Cool. Did anyone have any suggestions of things we could add to the paper? Any kind of topics we might have missed? We do need 3 more pages. Is that including references?
Yes.
Okay, cool. So 3.5.
Yeah, basically all you need is results. That's just what that comes down to, having results or not.
Yeah. So it's doable.
So it is doable. And if you miss that, there's a May 1st deadline, I think. Let's see.
Could you share your screen? I want to see the.
Yeah.
I want to see the thing. Is it an IEEE one?
So here.
Yes, it is.
Full length. It has April 18th as deadline, but if you miss it, there are other deadlines for May So we could always shoot for them. I actually don't
Huh.
know the
One
different.
page extended abstract.
Yeah, so I think they're different workshops.
Yeah. Let's do the. We can do the 4 one. We'd have to get results either way, for if it was extended or not. Like the 1 page extended abstract or 4 pages. And what is this called?
This is
Body
called
sensor network.
International Conference on Biomedical and Health Info.
Oh, okay. That
I
that's
put it on the
related.
chat. Yeah,
Okay.
it is. So there are, I think, 3 workshops: BHI, BSN. So either of them we could like double submit, I guess.
Okay.
Or maybe not, but we could shoot for either of them as well.
Oh, so for GANs, I've never used them. How many samples do we need? A lot?
Samples, you mean like data?
Yeah.
Yeah.
How many proteins?
Like more the better.
Yeah, more the more.
I know, but how many? Like, is 10,000 too little, or?
I don't know. I think 10,000 will be enough.
I think that's really
Okay.
dependent upon like how many features we're trying to learn and like the
Well, okay.
complexity of our models.
Well, I think these.
10,000 is enough. I think that's fine.
Okay. Okay. I might just do 20,000 to be safe.
Yeah, I was about to say 1,000. So.
Really? Oh man.
Yeah. Honestly, I think 1,000 will be like just enough. That's my guess.
In the paper that Jeff sent, they used 69,000, I think.
It must have been a good game.
They didn't use a GAN, they use an autoencoder.
Okay.
I think so. I could be wrong. I could be
You could do
very
a
far off.
comparison between GAN and autoencoder, where the input to the autoencoder is the result of the GAN. And then we can say proteinate pipeline. And then that will be our like selling pitch. It's an end-to-end implementation of removing noise and learning noise.
Okay.
Oh,
that'd be actually really cool.
We could have 2 teams that implements the GAN and also that implements the autoencoder. So that could speed up our work.
Okay. For this paper or for the next one?
Well, for this paper as well.
Okay. Has anyone used an autoencoder before? Besides Asami?
Yeah, I have.
Yeah.
You have? Have you made it in Keras?
I haven't made it in Keras. I did it from scratch.
Yeah.
Oh, that's cool.
So you can do it. You can do it in Keras then if you can do it from scratch.
Yeah, probably. Yeah, I would guess.
Lit. Okay. So then it'll just be the 70 by 70 by 70. Oh, Adam, an autoencoder. So an autoencoder, you take a high dimensional input and then you kind of send it through different layers. And then as you progress through the network, the layers get smaller. So then you get a low dimensional space, and then it funnels back out to that same high dimensional space that you've started with. And then what you can do is as you train the model, you compare the output to the input and you use that as a loss. And you can say, okay, so then can we get information down to a small number of features such that you're able to retain that information when you go back out, when you try to reconstruct it on the decoder side. You have the encoder side on the left that goes down to the funnel, and you funnel out. It's called the latent representation is the low dimensionality, and then it goes back out to the reconstructed from the decoder, and you can compare that to the original.
So it's a zip
file.
Sorry?
Yeah.
It's a zip file.
A zip file?
Yeah, I mean, it's like a dimensionality reduction thing.
Yeah.
So like,
but I guess the idea with tagging along with a GAN is you
can train an autoencoder to like do other things when it's compressing. Like it prioritizes certain features so that noise just goes away, right? And you're comparing the input to like what it should be when it's reconstructed.
Yeah. What would be the motivation for tagging an autoencoder at the end of the GAN's generator?
Isn't it to remove noise?
Yeah, so when you predict, when I said that, I was thinking when we predict the structure, there's going to be probably some mistake. let's treat it as noise, right? So you have all the predicted values, like predicted structures. And if you treat them as inputs that have noise in them, and we can put it into the autoencoder, I was asking to myself, okay, what could happen then? And then.
But you need to compare that to something. If you compared it to the proteins we already have, that wouldn't really tell you much because we're trying to generate novel proteins, right? Ones that don't already exist. Because if we just generate ones that already exist, that's just a one-to-one mapping.
Oh, yeah.
I think we should just still prepare maybe a GAN architecture. Sorry, a autoencoder architecture, because I think that'd be useful for like increasing the disarray of the atoms progressively. I think that'd be interesting, and that's something we wouldn't do for this paper because it just doesn't fall under the scope. But I think for now, maybe just focus on the GAN, and then Jeff, since we're not going to do autocoders now, would you want to do more of the theory because you already did the presentation
On the GAN.
Yeah.
Yeah, I wrote a little bit in the paper on
Okay.
GANs, but
I might have
can
missed
do some
it.
more.
Yeah, we want. I think I don't know how much you would do for background. I don't know. Depends on.
I don't think we need to do a whole lot about like Goodfellow's like original paper or anything. It's more important to do stuff like relate what it says in the paper about GANs and like how we're using that for our purposes. Like the whole like protein representation part and the methodology that can all include stuff about how we're using our GAN.
Okay.
Wait, how does that paper relate to ours?
Oh, the original GAN paper is like what the architecture we're using is based on.
Oh, okay, got it.
Yeah. Not this one, but Goodfellows, right? This one was a one related where they took decoy structures and put it into a autoencoder. But I don't think it. I think you could add to that by progressively making the structures more decoy.
Yeah, are you familiar with like hot field networks? Do you know what those are?
No, I'm not.
Yeah.
They're like, it sort of reminds me of like this, like we're basically perturbing an existing like latent representation to make it seem like this is like we're changing it. Like that's what you want to use the autoencoder for, Ethan, right? And like the energy it takes to go down to the native like fold, I guess.
So for the idea with the autoencoder isn't to change it. It's to take a decoy structure it's like a picture with noise and then reconstruct it so that it doesn't have noise.
Yeah, I thought you were dropping that instead, and you wanted to do something else with it.
No, that is what I like to do for the autoencoder idea, but for the GAN idea, it's for generating novel ones.
Okay.
Yeah, I know. So many different projects.
It's okay.
Yeah. Cool. So I'll generate data tonight. That won't be that bad. I have notes, and I think I have proteins.
Even if you could generate 1,000 rows, I think that should be enough for us to get started, right, Isamu? If we don't need to get the end results, we just need some data.
Yeah.
So we take in, and then to improve the performance or accuracy, we can generate 1,000 more.
For the deep network, for the deep part of the GAN, I know that my professor had notes on specific number of like filters he'd like to use because they correspond to biologically relevant things in proteins. I know he liked some numbers because you could relate it to some stuff in protein structure. So I'll search for that tonight.
Okay. Well, for now, I will just copy and paste again from
Yeah.
the documentation.
Okay, that's good.
That
What's this,
works.
Jeff?
Yeah.
This is the DC, like the deep convolutional GAN that you were talking about.
Yeah, that's something we'd want.
So we need to, if we're using that, then we should maybe just cite this paper instead of Goodfellows.
Yeah, probably. You can probably do both.
Sure.
Awesome. Cool. All right. All right. What else? Anything else, or does that really encompass everything? Is there any sections that people would like to take ownership of? I know we kind of went through that in the chat, and you mentioned something, or just that's still standing, but it's good for us to have a plan.
Maybe we could put on Slack like what everybody's doing.
Yeah, we can. If you have any questions on like what you can work on because you'd like to contribute, just speak up, mention something, and yeah, it'll be great. But by Sunday, good goal for a small to get some sort of results in, and I guess for the metric. Ooh. Okay, so we'd be
metric?
So we'd be evaluating the GAN based on. You'd be evaluating the discriminator based on its ability to. It's a classification problem, right?
Yeah, like real versus fake.
Yeah.
Yeah.
Like, it just treats the images you provide as real and generate it as fake.
Okay.
If we're generating new proteins, does that mean we're gonna have to like look at them individually and see whether they're like they make sense or not?
I don't
We
think
could
that's
probably
possible.
we could
Because like if the GAN, like we don't know that the GAN is gonna work in a way that we want it to.
Yeah.
No, we should think of a density metric, because if the proteins are all spread out, that if the atoms are all spread out, it doesn't make any sense. But if they're closer together, it's more likely that they'll make sense.
Can we work with smaller proteins first?
Like how big?
And like the smallest
10?
that can be.
Okay, we'll do 10.
Yeah.
10. I did 10. I'll generate 10. This is what I did. 10. I did 10 amino acids, 80% alpha helix composition.
I just wanted to test if
1,000
it
of them.
works. Yeah.
And I think that if we had some density metric, that would tell us a lot about. Is there any way to calculate 3D density?
I thought that was what you were like talking about when you're talking about like the bounding box of a protein, like that refers to the density.
I'm saying when you predict a protein structure, if you have something that is kind of just randomly distributed through if you just have points that are randomly distributed through a three-dimensional space, then that obviously will be less likely to correspond to a protein structure. But if they're more concentrated toward a centroid, the centroid of the protein, they're more likely to be a protein. So if you could use that as a cutoff, as a way to kind of disregard samples, because I don't know if you want to train, because what I don't want to have is I don't want to have the discriminator being trained on unbalanced data. Don't think that would be good. So you kind of want a way to just get rid of the bad, but that doesn't really help penalize.
We can see how it works and then do that.
You could set up the loss function to be the center to the distance to the center of that 70 by 70 by 70.
Yeah, I guess so.
So you penalize
the average center.
Yeah, so there are
Okay.
70 by 70 by 70 nodes, right? The 35 by 35 by 35 coordinate will be actually the middle point of that cube.
Yeah.
So you can calculate the distance and set up as a loss function.
Yeah. In reality, you calculate the centroid for each given sample. I don't know if that's possible, but that's what we want to do.
Yeah, we could do that, right?
It's like
Yeah.
the center of mass of the proteins, whatever.
Yeah, that's it.
Yeah.
Assuming that all atoms weigh the same. Yeah.
I don't think we should get too much into the detail and complicate stuff yet.
Okay.
Yeah.
Cool. All right. Any other questions before we sign off for the night? I get to generate some protein structures.
So priority is finishing the GAN, right?
Yeah.
And we're doing the autoencoder later. Is that right?
Yeah. Autoencoder later. That'll be, yeah, I think so.
Okay.
And I'll be generating structures tonight.
Pick the ones that are the smallest, the proteins that have the smallest number of amino acids.
Yeah, the
Yeah,
easiest
yeah,
ones.
it'll be 10 amino acids.
Because you don't want to have, actually, we're gonna work on 70 by 70 by 70 space.
Yeah, that won't be 70 by 70 by 70. It'll be like 35 by 35 by 35.
Oh,
Okay.
yeah.
We want to feel as little as possible initially.
Yeah, yeah.
That space. All right.
Yeah. And then
Oh, I'm sorry. Can we
Sure.
after this meeting, can someone like write down who's doing what?
yeah,
Just so I
we'll
won't be confused.
yeah,
'cause,
I
like,
know.
I was kind of in and out of this meeting because I was cooking my dinner. So
Yeah, can't blame you for wanting to eat. Done that a couple times.
We could do it now, or we could write it in chat.
It shouldn't take too
Yeah.
long. We could just do it now.
Yeah, do you want to keep it on the Slack instead of the GitHub?
Okay, yeah, we can put it on the protein nuts channel.
Yeah. So there can be a lot of overlap. Am I sharing everything, or is this? Do you see everything?
We see everything.
yeah.
Okay.
Yeah.
Oh no, they see everything. Okay. Cool. Protein nuts.
So if you want to create a message and maybe pin it to the channel.
One. Yell at me. Okay. Oh shit. And then we can add names. This is a good way. So what sections you want to do?
Oh, okay.
Yeah.
You won't be able to edit your message though.
I know. What are we thinking?
Do you want to
Maybe-
add ours now?
Yeah, I can add mine later. Maybe if you just type what you want to do right here and I'll append it, and then we can delete your message or keep it there or whatever.
Okay,
I think that's a good system.
like that.
Yeah, I like that.
Okay.
Good way. I like that. So Sama's doing results and GAN architecture.
Oh, I thought Jeff wanted to do that.
Oh, sorry. Yeah.
Yeah, I can do the background and then like how we're using the architecture and how it corresponds to like
Okay.
protein stuff. I'm probably gonna need to talk to you about that.
Oh, okay.
Sure. All right, Alicia. It can be another section too. I mean, these sections are pretty big. It's 4 pages.
I'm doing related work plus GAN. I just realized there are 2 channels, protein-net and protein-nets. And I'm in the protein-net, and I'm the only person.
That's so funny.
Because I've been putting some stuff like how to fix the bibliotecs. And
That's funny. And you said GAN architecture?
yeah, GAN with Isamu and Jeff. So GAN architecture, yeah.
Yeah, I'm gonna spell it wrong. It's fine. Oh, jeez. Thanks, Molly. I started a little bit writing about like the protein set, the data set. Oh, data set's 1 word or 2 word. I'll just do 2 words. encoding. What's so funny?
Oh, I joined Protein Net.
Switching sides.
That's funny. I mean, we're gonna need to have a couple of channels anyway, so.
I should. Yeah.
Representation. Okay, and what kind of figures do we want to include? That's a good point. So
Yeah, I was
maybe,
gonna ask how do you generate those 3D colored structures in the
oh,
paper?
I used
Oh,
yeah, I used
Adobe or
no.
is there a library for that?
Pymol.
That's
It's a way of
library, right?
yeah, it's a way of generating. It's a program, but you can. It's a way of visualizing. I might actually have it. Pymol. It's an application. I wonder if I have a data structure. I can show you. It'd be pretty cool. And you can change the atom colors, the bond colors. You can do a lot actually. It's a way to visualize structures. Let's see if I remember how to do it. Ooh, I just saw data that I wanted to include. Let's just go to projects. Data maybe? I don't know if this is gonna work. Oh yeah, right here. And then there's different, this is one CRN. You can do different, that's not there. It's like in show as spheres. That's not, show as dots. Show as, so, no, I'm just doing it. Lines, oh. You can basically show as a, sticks. Oh no, I'm just confused. Oh, now I really messed up everything. Oh no. Anyway, it's gone.
it looked nice in the beginning.
Yeah, it did look nice. There was a way to do it such that it just shows you a lot of information, and I use that to generate it. But I actually generated those figures from I predicted the protein contact map from amino acid sequences, and then I reconstructed it. Well, I aligned it. Sorry, I could reconstruct it, and then I aligned 3D structures, and that's what I exported to. I think it's a .ctf file.
Mm-hmm.
Yeah. Is there a way for me to just go back? Is there an undo button? Oh, nope. It's all gone. Yeah. Anyway, that's what I used. Cool. Adam, do you have a favorite section? Did he go off make dinner? Alicia can tell me what she wants to do later.
I'll get whatever's left.
Okay. Maybe in related work, if you want to talk a bit about maybe you and Adam could split maybe the background of protein structure prediction. There's a lot out there on predicting protein structure. There's not a lot on making the correspondence between function and structure, like generating novel structures.
With deep learning methods, or just okay?
In general, I don't think. Oh, and then what function? We have to have that's something else we need to do. We need to have a well-defined function. I know I said, I know I said cutting, right, as the original one, but I don't know if that's good enough.
Wait, until the one making a data set, so I think you can just select proteins that cut.
Okay, then I'll figure out how to do that.
Oh, I will feel free to share, but I think you're the only one who knows what you're
Okay,
talking
so I'll
about.
do that.
Yeah.
All right, I gotta leave.
Yeah, I figured.
But yeah, thank
Yeah.
you for all of these. I think this is good progress.
Yeah, good job, guys. We'll talk in Slack, and I'll see you next week. Not soon.
Yeah.
Thanks.
See ya.
Bye.
Bye.
I think Adam did make dinner.